Yeah, so last time we were doing differential forms. We talked a little bit about tensors and stuff. Let's see. I mentioned that D thing, the exterior derivative, is differentiating zero forms. But what does that really mean, right? You probably have like solved differential equations where you had to do something like take the total derivative. Right? So you take some function x, y, z, and you take exterior derivative of that, and you get a line integral, something like that. You get a one form. But what is that really doing? Let's look at how we might visualize that. So if you've got, let me think of how to do this. If you've got a function m mapping to n, call this f, and it's a smooth map. M and n are both smooth manifolds. Namely, this is dimension m, this is dimension n, so we have this property. Just distinguishing the dimensions of each of these manifolds. Then what you have as the, yes, okay, so last time when I talked about taking exterior derivatives of zero forms, I did maps from M to R, not from M to N, just a generic manifold or anything. So this is, in general, you can take any manifold, and you can take the exterior derivative of a zero form, or a smooth function. And what that looks like is you'll have Tm mapped over to Tn by df. And the idea is that this should commute. This diagram should commute. So this takes a tangent vector to m and maps it to the point at which the vector is a tangent, in the tangent space of. Maps it up to here, and then if you go over here through the map f, that's the same as having mapped through the differential map and then going up to n. But that's not really the interesting part. What's going on? Okay, so let's draw a little picture. Let's say I've got a map from R2 to R2. It might look a little patch of R2, and it might look something like this. You might have a coordinate system. So you got two tangent vectors here at this point. And F maps you over to here. Another copy of R2, and I'm just looking at a little coordinate system on it. And you've got your coordinate system here. Now, you can look at what happens if you take the x coordinate, that coordinate curve where y equals 0, and you map it. So this is, let's say, capital X equals everything in R2. So where you have x and 0 in R2 on the side. And you map that over to here, and depending on what f is, you can get any kind of curve. It might be up here. This might be f of x. Okay. So what is df going to do? Well, to this point, df should eat tangent vectors, right? So I should be able to take let's see. I should be able to look at the tangent spaces. So I should be able to look at this point, look at this tangent space, and you have a basis put on here by the coordinates in R2. So you have x and y. This is del x, del y in this case. This is del x, del y, and this is the tangent space to 0, 0 in R2. Okay. And these tangent vectors in here should be mapped over to here in some natural way. Now the idea is that f maps you from 0, 0 over to this point, and so we should have df being a map from this tangent space to 0, 0 to the image of 0, 0 over here. So you have f of 0, 0 right there. And you have its tangent space. Now, you might even look at it this way. It should be really a square, not a diamond rotated like that. Okay. And you have a coordinate system imbued on this by the fact that this point lives in R2. And it looks like this. Okay. So let's draw that here. This is again del x, del y. This lives in the tangent space to f, 0, 0 in this copy of R2. Now, where should these tangent vectors map to over here by df? Well, you just look at the function itself. You say, okay, well, I take this and I walk in this direction a little bit, and if I do that over here, then what's going to happen when I map points successively as I walk that way through f is I'm going to walk along this curve a little bit. If you walk a very short distance, you're going to go in this direction, tangent to the curve. And so naturally, that direction, you just project onto the tangent basis, and you get this vector. And so df is always a linear map. Okay? Always. And quite literally, if I defined what f was, I would be able to just take the exterior derivative of f manually, right? So df is always equal, in this case, to f differentiated with respect to x, dx, plus f differentiated with respect to y, dy. And you can just plug in a tangent vector here to this thing. Put in the point at which you're tangent to, and it will tell you what the image is here. So that's what we're doing algebraically when we calculate the exterior derivative. So we're figuring out how the tangent vectors, infinitesimally, what does walking along them look like over here in the image space. So that's the geometric interpretation of the exterior derivative of a zero form. Same thing, no matter, you might have this mapping from R2 to R3 or just R2 to R. It doesn't matter. It's always going to be the same interpretation. It's a linear map, always. And you can write it as a matrix if you like. So, what is a differential form talking about? What is the point of it? The origin was that they wanted to generalize, differential geometers wanted to generalize integration to arbitrary manifolds, and it kind of works this way. So give me some integral, like maybe on R2. Function you might have to integrate.
X squared y.
Okay. Dx dy. Right. Now you can pick out any region of integration you'd like to integrate this on. Okay. So usually they write R here, not like real numbers, but just some region in R2, or a domain even. And you're free to choose that, and then you don't have to redefine this thing. Now this looks kind of like a differential form. And it turns out that the way you define this is you write the same thing, but you put a wedge between each of the differential one forms, the basis points. And sometimes the convention is that people will write D here, and it just means the same area in R2. So let's say, like, I've got, in R2, I've got some kind of patch. I can integrate this function over this patch. And it's pretty easy to do so because I just come up with some parameterization of the patch, and then I do integration along X only, and then Y only. It's easy. But the trouble is, if I were to commute this, this would become negative. So that's x squared y dy wedge dx. Okay. But this would not become negative if I commuted. Right? Keep the value the same. So why is that? The idea is, when you write d here, you're taking an orientation for d. You kind of implicitly state that you're going to take the counterclockwise orientation. R2. If you're working in R1 and you're not on a closed curve, if you're on a closed curve, you just go counterclockwise. But if you are doing just a line integral, you have to actually say where the start and the end is to pick an orientation. Differential forms have this built in by nature of the algebra, right? If you commute the components of the wedge product, it anti-commutes, so it becomes negative. So they have a natural inbuilt orientation. The idea is this. You use the right-hand rule always. So if you write dx, dy, you can think of having written x tangent vector in that direction, and then y like this. So this is del x, del y. And then making a parallelogram. And then you put x first, so you go in that direction to start with. And then you just keep going around the parallelogram. And you get this orientation, counterclockwise. Okay? So if I had written dy first, I would go the other way. This works for three forms as well. You just get oriented parallelepipeds. And the idea is whatever region of integration you're talking about inherits the orientation from the way you write the differential form. So if I wrote dy wedge dx, that would be this orientation, the clockwise one. So the order you write your differential form in determines the orientation. You don't pre-select it when you choose the region. Also, I should say, if you write something like this, where this is a differential form, the orientation is chosen, the domain of this thing is chosen, right? Because you have it being differential form on some manifold, and this integration is over the whole manifold, so you don't really need to even write D. There's no such thing as anti-differentiation with differential forms. You're just actually integrating, taking the definite integrals. So that's how you differentiate. I mean, it's pretty natural. Just choose orientation that's obvious from your wedge direction, and then you just integrate like normal. If you haven't really gotten any new tool, okay. Let's see. So there is an example I give, which is that we want to put a differential one form on R2. So say alpha is equal to, what did I put? Negative y dx plus 2x dy. Okay. And we want to integrate this. So this is a differential form on R2. And I'd like to imagine what this looks like. Right? So it's some kind of swirling vector field, and it looks, let's do this in a different color. It looks like this. And it's not exactly a circular flow. Let's see. You end up going horizontally when you're on this axis, but you kind of go faster downward and then upward in this direction. So you have outward vertical flows are a little bit faster than circular. So this is what that form looks like. Right, you can see it's faster in the vertical direction. And then we would like to integrate this vector field on S1, which I'm defining to be just xy in R2, such that x squared plus y squared equals 1, the unit circle. Okay. So I want to integrate alpha on S1. Okay. How would you do this? Well, my definition so far doesn't really allow me to do this without, thinking of how to do line integrals in general. You can draw what this looks like. It's just this, and this has an orientation not picked out right. hasn't inherited from the basis to form the volume form on R2, which is dx wedge dy. So it gets this counterclockwise orientation on it. Okay. So to take this differential one form defined on R2 and leverage that to integrate on some submanifold of R2, I need to define what's called a pullback. Pull back that differential form by some function. Let me see the computation real quick. Okay, so we have a parameterization of the circle, g of t, and it's defined this way: cosine t sine t. Now I'd like to define something called the pullback of the differential form alpha by g. You write g star alpha. And this should be a differential one form on not R2 anymore, but on S1, on the image of g. So you might write S1, or you might write g of R. Parameterization. So the image of that parameterization. Now, this thing is defined in such a way to satisfy this property. If I take a tangent vector to S1, so let's see, I might write B, that's going to be equal to alpha composed dg of B. So what does dg do? It takes tangent vectors to R, right? Or rather to S1, and it maps them over to tangent vectors to R2. And you can imagine that if I took in some abstract space a tangent vector to S1, it would look like this. Well, it's just going to map straight to this in R2. The same point where we're living. Okay. How do you actually compute that? Well, let's do this. G star alpha is just a precomposition in some sense like this. So I need to compute, this is going to be kind of thing. We're going to get a differential one form on S1. So it should be in terms of the parameter t. Okay. So let me see the computation again. After you do it once, get comfortable with it, but okay. Let's pull back something other than alpha real quick, which is just dx. So g star, remember I pulled back a differential form of dx is going to be d, and then you take x and you just plug in whatever x is here. This is x for us, this is y. D cosine t, which is negative sine t dt. Easy. The pullback of dy would have been d of, I should say, this should have been x gt, like this. So this would be y with gt in it. This is the selector function for the y coordinate. So you get d sine t, which is cosine t dt. Okay.
Are we working from a definition for pullback here, or just?
Sorry?
Are we working from a definition for pullback here?
Yes, this definition.
Okay.
And I've kind of fudged this a little bit. It's a little bit strange. I think it should have a d here, but what you do is you take the coordinates and you just stub in and stuff. Right?
Yeah.
So I've got g, which is this. I want to know what g pullback dx is. Well, I just replace x with whatever the x coordinate of g is. It's like a precomposition. So So then now I can pull back this alpha. So G star alpha is going to be, well, that's going to have been negative G star to the pullback x linearly, y dx, plus G star x dy. Right, so I'm getting that from the definition of alpha over there. 2, sorry. And now I just precompose. So what is y? It's sine t. What is dx? Well, I already computed that. That's sine t. So sine squared t now, dt. Plus 2. And then you'll get cosine squared t dt. And that's all you can simplify by. Did we do that right? Yes. Oh, you can, I did something a little bit stupid, which is that this was supposed to have had another negative in it because of this. So that would have been like this, so then we can simplify and we just get dt plus cosine squared t. So that should be 1 plus cosine squared t dt, because I had another copy of cosine squared t dt right there. Now, the idea is if you've got, how does this work? This theorem's a little technical. So proposition. Let U and Rn be a region. That means, you know, an open set, or like at least part of a closure of an open set. And let G be a function from U to Rn, which is smooth. And it has to be a one-to-one map, and it has to satisfy the following condition. The determinant of the Jacobian of G must be 0 everywhere except on a measure 0 set. But these are just technical things. In practice, you just compute the thing, and it is easy. Basically, I mean, if you take a parameterization of a submanifold of Rn, that's G. And it should be a full dimension submanifold. And then you say, okay, if omega is a differential inform defined on S, which is equal to G of U, so the image, like the manifold that you're parameterizing, then you have the following. The integration on S, that parameterized submanifold of Rn, like the circle, well, I'm not doing a circle, but we might have like a disk in R2 or something, that would be S. Then you have this property. The integration of that differential 2 form on it is equal to the pullback of the parameterization, or pullback of the differential form by the parameterization on the whole domain. Okay. And you can generalize this and say the following. Because we want to do it for submanifolds of a different dimension than the whole space that they're embedded in. Okay. So if you have the following, you have U is in RK. So this K may be different than N. So you know, if in our case we have this being a parameterization of the circle, so it's going to be R1. And G, mapping from U, which is the parameterization, over to Rn is smooth. Okay. you also have the criterion on the Jacobian, being that it has to be full rank everywhere on U. So this should equal K on U. What that means is that your parameterization doesn't fold over on itself or anything. Except on measure 0 set, then we say that M, which is equal to G of U, is a parameterized K manifold living in Rn. And you have the following property. If you have a differential inform, or even a K form actually, you have a differential K form living in Rn, and you want to integrate it on M, that parameterized submanifold, the integration of it on there is equal to pullback by the parameterization on all of the parameter space. So let's actually compute with this now. That's the full proposition that you need to do calculations on submanifolds. So remember, this is our pullback. In practice, using it's much easier than writing out the propositions and stuff. Okay, so what are we trying to do? We're trying to integrate on S1 differential form alpha. Okay, so this is a parameterized submanifold of R2. So we've got the setup that we have over there, right? This is M. U for us is going to be something like 0 to 2 pi. Because think of our parameterization, it's cosine t, sine t. So we want to go full revolution. So we go 0 to 2 pi. And this has the orientation, which is just 0 to 2 pi to the right on the real number line. And let's see, I want to integrate the pullback there, and that's this. You can now write it in the classical way, which is like this. Okay. So that's your integration. And you can just compute this using elementary integration. I kind of want to show how you would integrate this with the knowledge of exterior derivatives and differential forms, because it changes how you do it from Calc 2. It's a little bit different. So how would we get the antiderivative of this thing? Well, firstly, you split and use the linearity of integration. And you say, okay, well, this is going to be 1 dt plus integration cosine squared t dt, okay, like usual. This you know. Integration of dt, the antiderivative, is just t plus c. And then you have this thing left over. But I can simplify this using the power reducing formula. So that ends up being 1 plus cosine 2t over 2 dt. You have a constant still in here, so I still don't need to write plus c just yet. And I'll come up here. And I have some trouble. I can use linearity again, and I can get t plus t over 2 plus this thing now, 1/2 cosine 2t dt. And this one isn't the greatest example, because I mean, it's just kind of obvious that d2t I would like to have. And what is this if you differentiate with respect to 2t? Or with respect to t, you get 2 times dt. And you can just divide by 2 on both sides. And then this is easy to solve. So 3t over 2, combining these two, plus 1/2. And then you have
cosine 2t dt 2t. And then you had another factor of 1/2 come out, so that, and then this is just the usual. In general, though, if you have something like this, sine t, cosine t, dt, when you do u substitution, you're looking at this to be the derivative of this thing. And what you can do is you can notice that this is a differential one form, and in some sense you can think like, okay, I can integrate this thing into the exterior derivative, and just think of taking that, like, and integrating it and sticking it inside of here, and then you don't have to write out like u equals sine t, du equals cosine t dt, and all this stuff. But it just makes it a little bit easier to think, okay, this is now sine t, d, sine t. And just working with differential forms, everything becomes a little bit more lubricated, and you can solve integrals like 50 times faster.
So when it comes to applying the bounds, do we always just sort of apply the bounds at the end and then like wait?
And calculate the number that comes out?
Yeah.
You'll always get a classical integral, except when you use the thing I'm about to show, yes, which is kind of the biggest result in differential forms, the Stokes theorem. So you can use that a lot of times, and it will just give you a result instantly, and you don't have to do this. But yeah, if you're just using the pullback, in general, you're going to end up doing this thing.
Yeah, okay.
You'll have a classical integral at the end. You get 3t over 2 plus, whatever, plus 1 over 4 sine t